everyone, I welcome you all to this presentation on packet header attacks on NoC, that is network on chip based tiled chip multi-core processors, that is TCMPs. I and myself Uday and my colleague Rishabh Raj both are involved in this project, and we both are from computer science department from Indian Institute of Technology Guwahati. And let's talk about hardware trojans. So an adversary means attacker or uh, can introduce a trojan designed to disable or destroy a system at some future time. Or trojan could leak the confidential information such as your secret keys or your passwords covertly to the adversary. So the trojans can be implemented as hardware modifications to ASICs, application-specific ICs, commercial off-the-shelf parts, microprocessors, microcontrollers, network processors, or digital signal processors, that is DSPs. So they can be implemented as firmware modifications also, like in FPGAs, the bit streams. So an IC fabrication process contains three major steps. The first one is design, which includes intellectual property IP, models, tools, and designers. And second is fabrication process. You can say it fab also. It includes mask generation, lithography, and packaging all the components together on a single chip. So after the fabrication step is done, the manufacturing tests are performed so that the chip behaves correctly.
The authenticity of the chip in design process, the intellectual property blocks, model and standard cells used by a designer and by foundry during the post design process are considered untrusted. The fabrication process might also be considered untrusted because an attacker should substitute Trojan IC for genuine ones during transit or could subvert the fabrication process itself by the implementing a Trojan into IC mask. Manufacturing test, if done only in the process test center by the client semiconductor company and government agency, would be considered trusted. There are two main options to ensure that chips used by the client and on client is authentic. Making entire fabrication process trusted in prohibitively expensive and nearly impossible with current trades in the global distribution of IC designs and fabrication steps. The second option is to verify the trustworthy of the manufacturing clip of an return to the client required defining a post-manufacturing step to validate the clip's conference with the original functional and performance specification. The consider and difficulty in detection of under attack. Generally, hardware-based security technology modify hardware to prevent attacker to protect IP blocks and secret keys. Here are the attacker to assume to misplace a filter to design before and during the fabrication. Detections of such attackers are extremely difficult to several reasons, like given the large number of short films and hard IP code used to system on chip, as well as its high complexity of today IP blocks, detecting a small malicious alteration is extremely difficult. Secondly, nanometer IP feature size make detection by physical inspection and detective reserve engineering very difficult and costly. Third, Trojan circuit by design are typically activated under very specific conditions. For example, sensing a specific design and such as power and temperature. The last one, fourth, test used to detect the manufacturing fault such as stuck at and delay fault cannot guarantee detection of Trojans. Now we are discussing the classification of Trojan. There are three major or mainly classification: physical, activation, and action. Now, in physical classification for distribution, structure, size, and type. Basically, type have a pyramidal and fractional type, and in activation classification, there are two: externally and internally activated. Internally activated two condition always on and conditional logically and sensational conditional. In externally activated uh, activated by the antenna, sensors, and many. And now in action classification that transmit information. They transfer the data to attacker, only transfer data to the attacker. But in the modification, classification and function, they change the data. And you see in TCMP, the component of a tiles are processor and processing elements. L1 instruction कैसे, L1 data कैसे, L2 कैसे, L1 कैसे controller, L2 dash कैसे controller. Tiles controller act as an intermediary between the cache controller and network adapter. L1 cache controller and L2 cache controller provide interface to the corresponding cache, while Tiles controller act as an intermediary between the cache controller and network adapter. Since L2 caches are shared and distributed among all 16 tiles, total set of L2 caches are uniformly presented across tiles in sequential fashions. NoC router consists of input port buffer routing units, virtual channel allocator, and switch allocator, and a crossbar. So now I will explain the internal architecture of TCMP. It consists of six tiles, and each of tiles are there one processing elements, one L1 data cache and L1 intersection cache, L2 cache, control for both L1 and L2 cache, and the tiles control and networks adapter. And on the right side, we have internal architect of NoC router, which have several ports, control logic units, and crossbar for exchanging path.
So now we will see the handling of cache miss in L2. So whenever there is a cache miss in L1, then the controller will forward it to the tile controller, and the tile controller computes the corresponding L2 tile number. So when the L2 tile number is same as that of the tile number of the tile controller, then it will be served locally. Otherwise, it will be forwarded to the network adapter to contact to the NoC. Network adapter, it is a thing, it is an adapter that is based on a message type, L1 miss request, L2 miss reply, etc., that creates and forwards the packet to the router attached to that tile. So a missed request packet, it consists of a single head flit, multiple body flits, and a tail flit. So here it is numbered from 1 to n body flits. So there are a total of n plus 2 flits. So when NoC follows wormhole switching, so the body flits will follow the head flit. So the router will compute the appropriate output port based on the underlying routing technique, whether it is a XY routing or other algorithms. So now we'll see the format of the head flit and the body flit. So the control channel will run in the parallel to the flit channel. So there are exactly two channels to handle the case. The FT field in both the channels is a common, and VCID field is also common. So these two fields are common in both the flits. So when FT is means the type of the flit, whether it is a head flit or other type of flit, and VCID is the virtual channel ID of the next downstream router. So VCID is inherited by all the subsequent flits of the same packet, and PID is the packet ID of the packet in the network, and SID and DIDs are the source ID and destination ID of the tile number, and this PL is the length of the packet, that is how many non-head flits are there, and the type is the type of the packet. What is the type of that packet, and PR is the rank of that packet if there is a port conflict, and CMD is used as a metadata for that flit, and address is the physical address to which the memory corresponding is required. So now we'll see the internal architecture of an input port buffer. So the input port consists of three virtual channels, and each virtual channel is a FIFO queue, and it can accommodate at most 3 flits. So a total of 9 flits can be accommodated inside a input port of a NoC router. Then the VC will separately maintain a control buffer, as you can see in the brown color under the main channel. So each VC will consist of a status, whether what is the status of that channel, length of the packet that currently being processed, virtual channel ID, and the output port to which the packet should follow. When a flit reaches a router, the router input port extracts the virtual channel ID from the common prefix of the incoming flit and places it to the designated virtual channel. If it is a head flit, then the length field of the packet is copied to the length field of the control buffer, and SE is set to be busy, status is busy. The route communication unit extracts the destination ID from the head flit to compute the next outgoing port, and output port is updated accordingly. So once the routing is done for a head flit, the output port holds the next outgoing port info for all the subsequent flits of that packet. So this will facilitate the wormhole routing. So now we will see the threat model. So the unavoidable plain text transmission of the head flit makes it vulnerable to hardware Trojan attacks. So this attack, which is randomly generated, it manipulates the head flit when it is residing in the input port virtual channel of the hardware Trojan infected router. So once the output port and virtual channel ID is computed and updated by the route computation unit and the virtual channel allocator unit, so the hardware Trojan modifies the destination ID field of the L1 cache miss request packets. So to facilitate this thing, the hardware Trojan checks the type field of the head flit, and if it is a L1 miss request packet, then it will modify the destination ID to a random destination ID such that the new destination ID can still be reachable by the underlying XY routing unit without any turn violations. So we chose R1 miss request packet for the hardware Trojan attack because L1 miss penalty impacts the processor throughout to a larger extent. So now we will see a illustration. Consider a L1 miss request occurring at tile number 4. So the miss request packet will be generated and it will be injected at the router number 4. So it is routed at the destination number 15. Therefore the destination ID should be set to 15. So as per XY routing unit, this packet passes through the router number 5. If the hardware Trojan in 5 is already triggered, it modifies the destination ID field to a random router. So in this case, they are routing it to 3. Since the hardware Trojan changes the destination ID after routing and virtual channel location, the packet will move to router number 6. However, at the router number 6, routing will be done for destination ID 3. So accordingly, the packet takes a south turn at router number 7 and reaches the router 3, and it will be injected into the tile number 3. But the packet will be dropped at tile 3 because the destination value calculated from the address at tile number 3 will not match with the destination ID of the head flit. Moreover, if the source of the packet expect a cache message from the 15, which will never come back because the 15 is unaware about such happenings. So here are 2 reference papers which we have taken for preparing this presentation. So thank you for your presence.